All right, so okay. All right, so good afternoon again. So as usual, I wasn't able to monitor the time, so that's why it forcefully closed our meeting. Anyway, so let me just check if you guys are already in front of your computers. So just give me a thumbs up. Okay. So 6 out of 13. Half of you are already here. So the others maybe are doing something. Okay, so just like what I'm saying a while ago, if we have the positive half cycle, we have this flow of current. Okay, so if D2 and D3 conduct, the opposite diodes D1 and D4 remain reverse bias. Okay, so this one is for the positive half cycle, and then the other one is now the negative half cycle. So the D1 and D4 is now activated, or they are now in a forward bias, but the D2 and D3 is now in a reverse bias. So as a result, this will now accept also a negative half cycle. Okay, so if you are going to combine those two, then you can have this kind of output. So we have the positive and then we have the negative. So don't get confused regarding with this one. This one is a negative half cycle. It's just that it was flipped, okay, into two just to make this VDC clear. So again, this VDC is our average voltage. So notice this one, that in a half wave rectifier we have 0.318, but in a full wave rectifier we now have 0.636. Okay, so let's go back on the BDC of the half wave rectifier. So this is the BDC. How you compute the BDC for the half wave rectifier? We have 0.318 times Vm minus Vt. But for the full wave rectifier, okay, we now have 0.636. So all you need to do is double that one. Okay, let me just check something. I forgot the computation. But uh, the 0.318 came from the with the computation of pi, because one cycle is 1 pi. Okay, and then half cycle, okay, or half wave rectifier computation is of course pi divided by 2. But I think there's another number. Okay, it's not just 1/2 of pi. But yeah, anyway, so yeah, so one cycle is 0.636, and then half cycle is 0.318. Okay, so if you have a voltage threshold on this one, then you have to deduct those two voltage threshold. So let's say you have two negative 0.7, okay, then you'll have negative 0.14 in here. Okay, so considering the VP of the diode, so if you are now going to have a voltage threshold, so as a result, just deduct that one on our peak voltage. Okay, so Vm minus twice the VT. Okay, so you can do this one if you have the same silicon diode on those diodes. But if you have germanium on the other one, so of course you have to change this one into negative 0.7 and then negative 0.3. Okay, negative 1 volt. All right. And as you guys can see, our graph now is now considering the voltage threshold. Okay, so for the first cycle, we have a deduction of 0.7. Okay, so it won't uh, permit a current unless you were able to give him enough voltage. Okay, so at exactly 0.8, that's the only time that it will permit a current. So the same with the negative part. So it will consume first the negative 0.7 before it will conduct a current. So are we clear so far regarding with this graph of a full wave rectifier with a voltage threshold? What about the others? Okay, great. So it seems like that half or most of you are able to get this one. Okay, so using silicon diode in a full wave rectifier. So here's the computation, or the how you uh, get the expression itself. So we have this one as depicted in the above figure. There's one right here. So if instead of ideal diode, a silicon diode is used, applying Kirchhoff's voltage law over the conduction line would give us the following result. So Vi minus Vt minus Vo minus Vp is equal to 0. And if you are going to simplify this one, it will give you this kind of expression. So Vo is equal to Vi minus twice of Vt. So that's where this formula came from. Okay, so of course it was derived from this circuit right here. Okay, and this will never change. So that is why we have uh, a constant formula when it comes to full wave rectifier, especially if we're talking about the four diode bridge rectifier, because there are other types of full wave rectifier, not just this four diode. So later on, I'll show you guys those different uh, types of a full wave rectifier. But yeah, so where are we now? So this is the formula for the voltage output for the full wave rectifier. And then when it comes to V peak, so this is how you solve it, of course. So V max is equal to Vm minus twice of Vp. So before it's just minus Vt, but in here you have, you know, you just multiply the Vt to 2, since you have the same voltage threshold or the same diode. But again, if your diode is not the same, so like the first one is silicon, the second one is germanium, then this will not be applied anymore. Okay. But anyway, the point is you have to deduct the voltage threshold of your diodes. Okay. And as usual, of course, your voltage input must be, greater than twice of your voltage threshold. So you must have 1.5 volts and above if you have two silicon diode, okay, or 0.7 volts and above if you have two germanium. Okay, so we can use our earlier equation to get the average value with a reasonably high degree of precision, which is, VDC is approximately equal to negative 0.636 Vm minus twice of Vt. Okay, so just double this one and then just double this one also. So let's now talk about PIV, or peak inverse voltage, or sometimes they call this one PRV, or the peak reverse voltage. So I think this one is very straightforward. If we have, let's just go back right here. So if we have a peak to peak voltage, so when we say peak to peak voltage, it is the value of your positive, okay, peak value, and then the uh, peak value of your negative uh, result right here. So it could be positive or it could be negative, but of course, those two are just the same. Okay, so that we call that one peak inverse voltage, or the peak reverse voltage. Okay, so it is basically a reverse bias voltage range of the diode that must not be exceeded. Okay, otherwise the diode may break down by transiting into a region called Zener avalanche region. So this is now the one that you are talking about, Mr. Jean Alexis. So the breakdown voltage can be only attained if we have a reverse bias connection. Okay, so if you exceeded that voltage, then we're going to have a avalanche or Zener avalanche region, wherein going to have a uh, current that will flow on that one, okay, instead of just a completely open circuit. So we're going to have more examples on that one, I think, on final. So for now, it says here that PIV rating is greater or equal to Vm. Okay, so we can only attain that one if we have a higher, or at least, oops, what is this? Or at least equal to your peak voltage. Okay, so this one is only for a half wave rectifier. Okay, So let's continue about the full bridge rectifier. So for a full bridge rectifier, also the PIV rating calculation is the same as half wave rectifier. That is PIV, which is greater or equal than VM, since VM is the total voltage that's applied to the connected load as depicted in the following figure. Okay, so this is where you can solve the maximum voltage, and then the inverse of that one, or the reverse, is at this point. Okay, so if you have higher, okay, or at least equal, then maybe you can attain that peak inverse voltage reading at this point. Okay, but if it's just a peak voltage, then it's always on the RL, or the resistor right here. Okay, so let's have another example. So problem number 3, full bridge rectifier network. Determine the output waveform. Okay, I have this one for the following diode network, and also calculate the output DC level and the say PIV for each diode in the network. So let's answer this one first. So what is our output waveform? Is it just the positive half cycle? Is it just the negative half cycle? Or is it both? So this is our voltage input. We have a peak voltage, or a VI of 10 volts. So what is it? What is our output waveform? Is it a full wave or just a half wave waveform? Anyone who would like to guess? So wala. Okay, let me call someone. Miss Grace, since ikaw yung may picture na nakita ko agad. Miss Grace Ginaran, are you around? So I think she's not around. Okay, what about you, Mr. Christian Kenneth Torres?
Wait, sir. Di ako sigurado kasi, sir.
Hindi ka sigurado. Well, it's just
Yes,
a
sir.
guess. Okay, so malay mo, tama yung instinct mo. Is it a full
Sir,
wave
half.
or half?
Sir, half.
The answer of Miss Grace is also half. Your answer is half. Okay, what about the others? Is there anyone here saying that the result is uh, full wave? Ayun. So lahat kayo half wave. So lahat din kayo mali. Okay, so I think it's super obvious. So if we have the positive half cycle, let's say at 10 volts, of course it will flow in here. Okay, and then regardless of it will go here or will go here, it will go back on the VI. So we have a complete half cycle for the positive. And then let's say we now have a negative input, okay, on this circuit. So of course it will now go on the left side. So again, regardless of the current will go here or go here, so it will end up and then going back on its original source. So as a result, we have a circuit which accepts both the positive and negative half cycle. So this one will give you a full wave output waveform. Okay, so this is the solution. Where is that one? Here. Okay, so here is the complete cycle. Okay, so the next question, why is it only 5? Why is it not 10? go back here. Why is our VO divided into 2? Why is it not 10 anymore? What is the reason behind that? Anyone who would like to guess? Okay, let me call someone again. Miss Jennifer Ann. Mr. Miss. Yeah, Miss Jennifer Ann Baltazar. Sabi ko kanina, Mr. ba nasabi ko? So, I think she's not around. Anyway, how about you, Mr. Mark Tanikala? Are you around? Or you are somewhere else? Wala din. Okay, what about you, Mr. Nathaniel? Nathaniel Estalibia.
No idea, sir.
No idea. Why is it 5? All right. What about you, Miss Maris? Miss Maris.
I think yung
yes.
half is dun sa negative mapupunta. And yung half, sir, is dun sa other half niya.
Saan? Pardon. Kakapalakas ko lang ng volume ko.
Sir, yung, di ba, 10 voltage siya? And yung 5 voltage is napunta siya dun sa other half, and yung 5 is napunta po dun sa other half. Something like that.
Okay. Okay, so there is a message. Sir, the half is the off. The other half is on. No. Okay. So, ganun pa rin. We still have a complete 10 volts. Okay. After passing through this diode. Okay. Still have 10 volts right here. And then we still have 10, let's say negative 10 volts at this point. Okay. So, your assumption, Mr. Jean Alexis, is not correct. Coming from Mr. Carlo, sir, I think half kasi sir yung voltage. Half kasi sir yung voltage. Okay. Anyway, so the answer of Miss Maris is actually correct. Okay. So if you guys are going to take a look on this circuit, kunin na lang natin lahat. Ulitin ko. Okay. So if we have a positive half cycle, so we have this flow of current. So let's use spread for positive. Okay. So at this point, it's still 10 volts. Okay. But then again, as you guys can see right here, our voltage will now be splitted into 2, since we have the same resistance. We cannot apply the smaller resistance, the lesser voltage drop. We cannot apply that one anymore, since we have the same value in here. So as a result, 5 volts will go here, and then the other 5 volts will go here. So our reading in VO is at this point only. Okay, not at this point, but at this point only. So at this point, we only have a reading of 5 volts. Okay, and then babalik siya dito, and then going back. As a result, in total voltage drop natin is 10 volts. But since our reading in VO is at this point, so we only have a reading of 5 volts. So the same with the negative portion. Oops. Okay, so let's use gray. Is it still visible? Brown na lang. Okay, so if we have negative half cycle, so negative positive, so this now will become on, and this will be off. Oops. So the flow of current will be from here to here, and then it will be splitted into 2. So at this point, we still have 10 volts, and some of the currents will go here, and then some of the currents will go here. So as a result, it will be divided into 2. So 5 volts here, and then 5 volts here. Okay, so I hope this one made this example clear on why we only have a reading of 5 volts, not 10 volts. So here is the solution. So that's here VO is equal to 1 half VI is equal to 1 half VI max, which is now equal to 1 half 10 volts. Okay. Oh, this one is quite confusing, but yeah, this one came from this redrawn circuit. So as a result, we have this one. So some of the current will flow here, and then some of the current will flow here. But I think this one is a lot easier to understand rather than having this rather than having this kind of circuit. Okay. And why we have 5 volts only. Okay. And the last one is the VBC. So since we have a full wave rectifier, okay, so you're going to use this formula, 0.636, okay, times 5 volts is equal to 3.18, okay. Or if you want to use the half wave rectifier formula, okay, so just half that one in two, okay. So you can also do this one, but this one will only confuse you, but this will give you the same result. So 0.318 times 10 volts. So this is only applicable, okay, this one right here is only applicable if we have this kind of setup. Okay, so this is still a full bridge rectifier. It's just that your voltage input will be divided into two. Okay, so having two resistors only, and then the rest are two diodes only, and then the rest are resistors. Okay, so the absence of two diodes in the bridge results in the reduction in the DC output with a magnitude of 3.18 volts. Okay, so I hope we're clear with this example right here. So any questions so far? For clarification? Okay, so I guess none. So let's now proceed to the another type of full wave rectifier, which is called the center tap rectifier. So in here, you are now going to need an inductor. So we have here the first inductor, which is called the primary winding, and then the second inductor, which is called secondary winding. Okay, and then this one right here is called center tap because this one is the ground, or where you going to read the voltage output. So later on, you're going to see the complete schematic or circuitry of this center tap rectifier. But yeah, so it has another two wires right here. Where is that one? So the wire is adjusted in such a way that it falls in the exact middle point of the secondary winding. So the wire is exactly 0 at volts of the AC signal. So this wire right here. So this wire is known as the center tap. So that's the reason why they call this one a center tap. Yeah. So the center tap transformer works almost similar to a normal transformer. Okay, like a normal transformer, the center tap transformer also increases or reduces the AC voltage. However, a center tap transformer has another important feature, that is the secondary winding of the center tap transformer, which divides the input AC current or AC signal VP into two parts. So this one is mostly used into increasing or reducing the AC output. So yes, you're still going to have an AC output, but you can divide it into two, okay, or divide it into three, or you can increase that one. Okay, you can increase it into two, increase it into three, or increase it into four. Okay, so that is why later on you guys will see a proportion right here, or ratio and proportion, like we have a 1:2. Okay, so if we have 1:2, if we have 10 volts, it will become 20 volts after passing through this secondary windings. Okay, so we call that one increasing, or increases the AC voltage. But if we have 2:1, then it will be divided into two. So that one now is decreasing part or reduces the AC voltage. Okay, so here is the complete circuitry. Okay, so we still have the positive cycle and then negative cycle, okay, for the voltage input. And then here is the output, so still the same. Okay, so it's just that you're not only going to use two diodes. Okay, we have the diode on the upper and then the diode below, and then the RL, okay, one resistor only on this center tap wire. Okay, so I will skip most of the part in here, since there is just an explanation on where is this connected, etc., etc. But if you want to get the V total, okay, so just get the computation part on the V1, which is the positive half cycle, and then the V2, which is the negative half cycle. So as a result, it will give you the V total. So where is it one? So V1 and V2 are equal in magnitude but opposite in direction. That is the voltages of V1 and V2 produced by the upper part, secondary winding R100. So in here, so take a look on this one. So most of the full wave rectifier, okay, is 180 degrees out of phase with each other. So meaning if we have a positive half cycle, okay, of course it's going to have a 180 degrees turn around for the negative half cycle. Okay, but okay, by using a full wave rectifier with center tap transformer, we can produce the voltage that are in phase with each other. Okay, so basically, if we have a positive 10 volts right here, we can actually combine those two. So instead of having a negative 10 volts right here, we can have a positive 20 volts. Okay, so that's the function on why we have this kind of circuitry, because it can double, okay, the voltage input into two. Kaya nga double eh. Okay, but sometimes it's not just double. It could be triple or it could be quadruple. So depending on how many inductors you're going to put in here, okay, depending on your second windings or secondary winding. Okay, so I encourage you guys to watch more YouTube examples when it comes to center tap. Okay, so ito yung para makikita nyo lagi sa mga transformer. Okay, so now from a super high voltage into a smaller voltage. So by using a fully rectifier with center tap transformer, we can produce a current that flows only in a single direction. Okay, so we can have, let's see, positive only or negative only. Okay, so more explanations when it comes to a center tap rectifier. So I think nothing is new, so I will leave the reading part to you guys, and then continuation. So I'll just mention the things that needs to be mentioned, but most of them are just explaining the connections. Okay, and then how is this positive half cycle work, and then how is this negative half cycle work. Okay, and then as a result, we have this as our input, we have AC input, and then this is the current for the V1. So obvious naman, I've already mentioned this one a while ago. So the upper part is your positive half cycle, and then the lower part, which is the D2, is the negative half cycle. So if you are going to combine those two, you're going to have this kind of result, okay, which is the full wave rectifier. Okay, so can you guys follow so far up to this point? Or do you have any question?
Wala naman to, sir.
Okay, so just let me know if you have a question, since I've skipped a lot of slides, but yeah, most of them can be understood after I'm reading them. So again, I will leave the reading part to you guys. So thus, a small voltage is wasted at the diode. So this one is the same with what we have in a 4-diode full wave bridge rectifier. So of course, we're going to have a waste of voltage, because diodes always consumes a certain amount of voltage. But then again, this voltage is very small. So as a result, this voltage is always neglected. Okay, and let's have last example. Okay, so in here, take a look of this one. So from here, you already know what will happen. So we have a 1:2. So we have one inductor right here, but we have two inductors on the secondary winding. So in other words, the more windings, the more inductors, okay, the more that it can increase the voltage input. So from 1, okay, which is 10, it will be doubled, which will give us a 20-volt result for the voltage output. Okay, so this V2 right here is the value of the secondary winding. So V1 is the input for the first winding, and then V2 is the output already. Okay, so this is the peak-to-peak voltage that you can have after passing through this, the silicon diode and then this another silicon diode. And then for the peak inverse voltage, we have this twice of Vm. Okay, so this is a default formula. So twice or 2 times V2 minus Vt is equal to 2 times 20 minus 0.7. Okay, so you can compute the inner side first. So 20 minus 0.7 is 19.3, and 2 times 19.3 is equal to 38.6 volts. So this is the peak inverse voltage. Okay, so more than that, again, it will result into a breakdown voltage. So this is the safe inverse voltage for this kind of voltage input. Okay, and then here are the formulas. Okay, just in case we need to summarize everything. So when it comes to peak inverse voltage, so we only have this formula for the half wave. So whatever is a value of your Vm, okay, that's already your peak inverse voltage. But for the center tap, so just double that one. Okay, your peak voltage, so twice of Vm. And then for the full bridge rectifier, so it's still Vm. Okay, and here. Okay, so this is where the 0.318 and then the 0.636 came from. So Vm divided by pi, okay, or twice of Vm divided by pi for the center tap, or twice of they are the same for the full wave rectifier. Okay, so here is the reference of this presentation. So are we clear so far? Any question regarding with module 3?
Yes, wala naman sir. Clear naman po.
Okay, so again, just a reminder, all of my examples are just the basics. Well, you can find them most of the articles, okay, all about circuits, Sun Foundry, electronic tutorials. So I would like you guys to explore more, okay, find more complicated circuit, okay. So you can base it maybe on this three URLs right here, these three links. So just try to answer them. Okay. So hindi naman ganun kahirap yung magiging exam nyo. So midterm exam nyo na after that, of course. May konting twist lang. Okay. May mga twist lang. So they are still super close with my examples or with your quizzes. Okay. So hindi naman siya ganun ka-complex. Anyway, so again, reminding everyone that you have additional 3 quiz for this chapter or this module. And we have additional 1 case study. So case study number 3 for this module. Okay. So next meeting, I will just announce, and then we'll be having a votation if we're going to have an advanced discussion regarding with the clippers. Okay, so hindi na to magiging part ng midterm exam nyo, but of course, sa finals na. But if you guys would like to, discuss this one next meeting, this coming Friday, we can do that one. Okay, so there's a question. So, sir, what type of quizzes? It's always like fill in the blank. Okay. Fill in the blank. So, It's not a multiple choice. So kayo mismo maglalagay ng sagot. Okay. So again, you don't need to put the units anymore. Okay. Naka-indicate naman lagi doon kung ano yung unit na ilalagay nyo. I mean, yung hahanapin nyo. So if it's milliamp, then dapat yun yung value na ilagay nyo. But if it's in ampere, dapat yun din yung value na ilagay nyo. Okay, so kahit na tama yung sagot mo pero mali yung format itself, so mali pa rin yan. Okay. Alright, so any other concerns? By the way, to those who haven't made their 1-minute video yet, please submit them as soon as possible. So you can also add maybe your expectation to your instructor, to me. So the things that I need to change, the things that I need to improve maybe. Okay. So, or kung ano man yung mga recommendation nyo, okay, or additional comments. So I would love to hear them. So kahit negative, okay lang. Ako lang naman makakapanood at makakarinig. Hindi naman nila ano ba nila to? Hindi natin nila makikita to. Ako lang yata nakakita. Yeah. So, okay lang. Labas kayo ng sama nyo ng loob. Alright, so if you guys don't have a question or clarification anymore, then meeting is now adjourned. Okay, and then just wait for my announcement. Okay.
Bye, sir.